All right, now let's talk about mole fraction. Mole fractions are going to be represented using the Greek letter chi. And let's talk about how one would go about calculating a mole fraction. In an example here, we're told that we have a mixture of 4 moles of O2 and 6 moles of N2. And let's figure out how we would calculate the mole fraction of O2. The idea behind this is to find the mole fraction of O2 in this case, we would find the number of moles of O2, and then we would divide it by the total number of moles. That's what a mole fraction is. And so in this case, the number of moles of O2 is 4 moles, divided by the total number of moles is we've got 4 moles of O2 plus 6 moles of N2. Importantly, mole fractions are always unitless. The moles on the top cancel the moles on the bottom. So what we can say here is that we have a total of 10 moles of gas, 4 of them are O2, and so we have that the mole fraction of O2 is 0.4. Or another way of saying that is 40% of the moles of gas are oxygen. Then we could do the same thing for the N2. The mole fraction of the N2 would be equal to the number of moles of N2 divided by the total number of moles of gas. And so for the N2, that was 6 moles over the total is 10, right? 4 moles from the O2 and 6 moles from the N2. And so the mole fraction of N2 is 0.6, or another way of saying that is 60% of the gas is N2. Importantly here, all of the mole fractions in a mixture must add up to 1. Everything has to add up to 100% of the total here. Now let's talk about how mole fractions can be related to Dalton's law of partial pressures. Another way of expressing Dalton's law of partial pressures is as follows. When you have an ideal gas mixture, the partial pressure of each component in the mixture can be calculated by taking the total pressure and multiplying it by the mole fraction of the component that you're looking at. Okay, so the partial pressure of component A is equal to the total pressure times the mole fraction of A. All right, with that in mind, let's extend the example that we looked at on the last slide. We have the same gas mixture from our previous problem, and we're now told that the total pressure of this mixture is 475 torr. And we want to know what the partial pressure of the N2 is. That's going to be found by saying that the partial pressure of the N2 will be equal to the total pressure of 475 torr times the mole fraction, right? That is the percentage that is the N2. We found in the previous slide that the mole fraction of N2 was 0.6, right? 60% of the gas was N2. And so the partial pressure of just the N2 would be 285 torr. Additionally, we can find what the partial pressure of O2 is from this equation. We can say that the partial pressure of the O2 is equal to our total pressure of 475 torr. And we're going to multiply that by the mole fraction of O2. We found that 40% of the gas was O2, so multiply by 0.4, that's our mole fraction. And the partial pressure of the O2 is 190 torr. That's how we're able to use this form of Dalton's law to acquire what the partial pressures are in a mixture if you know what the mole fractions are. And importantly, one more thing that's nice to show for the sake of completeness is that the total pressure can be found by summing the two partial pressures, right? We saw this at the beginning of our discussion of Dalton's law. P total is going to be equal to PO2 plus PN2, 285 torr plus 190 torr, all adds up to 475 torr, which is the exact number that the problem told us as the total pressure. It's nice to see how all of these equations relate and how you can kind of use them interchangeably depending on what the problem is asking for. That brings us to the end of this section, and next we'll talk about kinetic molecular theory of gases.